Welcome to this video tutorial on the full wave rectifier. In this video, we'll take an in-depth look at what a full wave rectifier is, how it works, and why it's important. We'll explain each component, the process of rectification, and examine the resulting waveforms to give you a comprehensive understanding of this essential electronic circuit. Let's get started. Introduction to rectification. First, let's understand the basic concept of rectification. Rectification is the process of converting alternating current, or AC, to direct current, or DC. AC is the type of current you get from your wall outlet, where the voltage periodically reverses direction. DC, on the other hand, flows in one direction only, which is the type of current used by most electronic devices. Components of a full wave rectifier. A full wave rectifier uses several key components to achieve this conversion. Let's go over them. AC source. This is where our alternating current originates. In this example, we have an AC source with a frequency of 40 Hz and a maximum voltage of 5 volts. Diodes. Diodes are semiconductor devices that allow current to flow in only one direction. Our circuit uses 4 diodes arranged in a specific configuration called a bridge rectifier. Load resistor. This is where the rectified, or converted, DC voltage is applied. It represents the device or component that will use the DC power. Oscilloscope probes. These are used to visualize the voltage waveforms before and after rectification. How the full wave rectifier works. Let's break down the operation of the full wave rectifier step by step. AC input signal. The AC source provides a sinusoidal waveform that alternates between positive and negative voltages. The waveform oscillates at a frequency of 40 Hz, meaning it completes 40 cycles per second. The maximum voltage of the waveform is 5 volts, so it swings from plus 5 volts to minus 5 volts. Positive half cycle. During the positive half cycle of the AC input, the following happens. The top end of the AC source is positive relative to the bottom end. Current flows from the positive terminal of the AC source, through diode D1. From diode D1, the current flows through the load resistor, creating a voltage drop across it. The current then continues through diode D2 and back to the negative terminal of the AC source. During this time, diodes D3 and D4 are reverse biased, meaning they do not conduct any current. As a result, the load resistor experiences a current flow in one direction, creating a positive voltage drop. Negative half cycle. During the negative half cycle of the AC input, the following happens. The top end of the AC source is now negative relative to the bottom end. Current flows from the positive terminal of the AC source, which is now the lower end, through diode D3. From diode D3, the current flows through the load resistor, again creating a voltage drop across it. The current then continues through diode D4 and back to the negative terminal of the AC source, which is now the upper end. During this time, diodes D1 and D2 are reverse biased and do not conduct any current. Even though the AC polarity has reversed, the current through the load resistor is still in the same direction. This is the key to full wave rectification. Output waveform. The output across the load resistor is a pulsating DC voltage. Let's understand this waveform better. The output voltage pulsates because it reflects the positive halves of both the original positive and negative AC cycles. The frequency of the output waveform is double that of the input AC signal. Since our AC source is 40 Hz, the output frequency will be 80 Hz. The maximum output voltage is slightly less than the peak input voltage because of the voltage drops across the diodes. Each diode drop is typically around 0.7 volts. Visualizing the waveforms. To visualize this process, we use oscilloscope probes. Input waveform. On the left side of the screen, you can see the sinusoidal input AC waveform with peaks at plus 5 volts and minus 5 volts, oscillating at 40 Hz. Output waveform. On the right side of the screen, you see the rectified output waveform across the load resistor. This waveform is now pulsating DC with peaks at approximately 3.728 volts, and it oscillates at 80 Hz due to full wave rectification. Conclusion. A full wave rectifier efficiently converts an AC input into a DC output by using both halves of the AC cycle. This makes it more efficient than a half-wave rectifier, which only uses 1/2 of the cycle. Understanding this process is crucial for anyone working with electronic circuits, as rectifiers are fundamental components in power supplies and many other applications. Thank you for watching this tutorial on the full-wave rectifier. We hope you now have a clear understanding of its operation and importance. If you have any questions, feel free to leave them in the comments, and don't forget to subscribe for more educational videos.